Example 4 is more like one you would encounter on a test. And it's a one-dimensional net force problem. So what do we have here? We have Io, which is a moon of Jupiter. We have Jupiter and the sun. And it says on one particular occasion, the sun, Io, and Jupiter lined up in a straight line so that both the sun and Jupiter were pulling Io in opposite directions. In opposite directions. So therefore, and it says using the information given on the chart, determine the net force acting on Io at this time. If they're pulling Io in opposite directions, here's the sun. Here is Jupiter. Io must be here because they're pulling Io in opposite directions. So in other words, Io is getting pulled this way by the sun and this way by Jupiter. If we put Io on this side here, it would be getting pulled in the same direction by both the sun and Jupiter. So it must be in between them. And we want to find the net force. So we have two forces acting on Io in opposite directions. One's positive, one's negative. And all we need to do really is find the force between the sun and Io, find the force between Jupiter and Io, and then add them as vectors. So it's pretty straightforward. You just got to be careful with the big numbers and the exponents and putting things into your calculator. Let's do the force of the sun and Io. And actually, just before we do that, let's think about what the answer could be. Which one is attracting Io more? Well, given that Io is orbiting Jupiter, obviously its gravitational force is stronger than that of the sun. But how much more? And I do this just so we can talk about exponents and relationships, how many times greater one thing is than the other. Let's look at the mass of the sun and the mass of Jupiter. The mass of the sun is 1.99 times 10 to the 30. The mass of Jupiter, 1.9 times 10 to the 27. So how many more times massive is the sun than Jupiter? People might look at those exponents and think, oh, it's 3 times greater, right? Because one exponent is 27, one exponent is 30, 3 times greater. But that's not the case, because remember, we're talking about exponents here. So that's 1.90 times 10 to the exponent 27. And when we're talking about exponents, to figure out how many more times greater, we're going to subtract the exponents to give us 3, and then that's 10 to the exponent 3. And 10 to the exponent 3 is a 10 times 10 times 10, which is 1,000. So in other words, just by looking at the exponents very quickly, we can determine that the sun is approximately 1,000 times more massive than Jupiter. So in terms of mass alone, the sun is going to have a much bigger gravitational force on Io. But what about the distance? Let's go over the distance. Use that same principle here. 11 minus 8 is 3, 10 to the exponent 3. So Jupiter is 1,000 times, or let's say the sun is 1,000 times further away from Io than Jupiter is. And since that distance gets squared, we can clearly see that the sun's mass is no match for the great distance that it is away from Io, and Io being so close to Jupiter. So clearly Jupiter's going to win, but by how much? So anyway, let's go through the calculations, and it's just a matter of plugging in the numbers correctly. So we're doing first the sun and Io. So here's the mass of the sun, the mass of Io, and the distance between them. So G times the mass of the sun times the mass of Io. What was that, 22? I hope. Let's go back up. Io, yeah, right there, and then the distance. That was 11. Square it. Okay, and again, make sure you plug that into your calculator correctly. Put brackets around this, and then put the squared on the outside so that you don't have any issues there. Do the top first. Press equals, and then go divided by bracket this number and the bracket squared, and that should give you the correct answer. And that correct answer is 1.86335 times 10 to the 19 newtons. So pretty big force between the Sun and Io. Then we're going to do exactly the same thing, but this time between Io and Jupiter. So the force between Jupiter and Io, and that would be, let's just abbreviate here. What was the, did I make a mistake on the mass of the Sun? 1.99, nope, 1.90. 0.90 times 10 to the 27, 5.93 times 10 to the 22 divided by 4.22 times 10 to the 8th. Again, don't forget to square it. Right? And you're going to end up with 6.35486 times 10 to the 22 newtons. So there we go. We've got two forces acting in opposite directions. And once again, you may look at those and go, oh, one's 10 to the 22 and one's 10 to the 19. They're not that different. Well, of course, they're that different. They're 1,000 times each other. So the force of Jupiter on Io is about 10 to the exponent 3, subtract the exponents, is about 1,000 times greater than the force of the Sun on Io. And then when you subtract those vectorially, you're going to get the net force. So the net force, therefore, equals, let's do this one first. Whoopsie, I forgot all the times 10 to the 22 plus negative 1.86335 times 10 to the 19. When you add those or subtract them, essentially what you're doing, you're going to end up with this number here, 6.35 times 10 to the 22 newtons. And you can see that this number here is just so small compared to this one that it's almost irrelevant. I mean, of course, it is relevant. It is going to, the Sun is going to pull Io towards it, but only by a very, very small amount, to the point that it's almost negligible. So that's the answer, and that would be towards Jupiter would be the answer to that question there. Okay, and we're not going to do this example, but just so you're ready for it on a test, you may get a similar question to that one, but in 2 dimensions. So a 2-dimensional example of that would be something like this is Io, Jupiter is down there, and then the Sun is here. And they may ask you, what is the net force on Io, or what is the net force on Jupiter? Right? And depending on, well, let's say if they want you to find the net force on Jupiter, then you're going to have to say that Jupiter is being pulled this way by Io, and it's being pulled this way by the Sun. Now notice I drew the black vector much, much smaller. Why? Because clearly the Sun is so far away that the force on Jupiter is, again, almost negligible. So when you add those vectors, you place them tip to tail, and then the resultant is tail, tail, tip, tip, right? And this is the force, this black vector is the force between Jupiter and the Sun, and the blue vector is the force between Io and Jupiter, and then you've got your resultant, which is the purple vector. So let's do it in the purple, and the resultant angle. So that's how you do that one. It's just a two-dimensional vector problem. Okay, so that ends lesson 29.